Good afternoon. I welcome you to the session of experimental methods in fluid mechanics, and today we will discuss about another flow measurement technique, that is the instrument, rather the operational principle of the laser Doppler anemometry. In fact, this laser Doppler anemometry is an important non-invasive flow measurement technique, and it is largely used to measure the flow velocity at a point. So, we will discuss today this laser Doppler anemometry. As I said that laser Doppler anemometry is an important non-invasive flow measurement technique which is used to measure point flow velocity at a point. Now, there are a few non-invasive techniques like so this is LDI in short, or sometimes it is also known as laser Doppler velocimetry. Or LDV in short. Now, there are different other techniques which are non-invasive in nature and also used to measure the flow velocity, like I can say LDA is one of them. So, LDA, then we can have PIV, that we know, that is particle image velocimetry, then we have MRI, magnetic resonance imaging, then we can have RPT. So, there are several other non-invasive measurement techniques available which are used to measure velocity at a point. So, this is particle image velocimetry, this is magnetic resonance imaging, and this is radioactive particle tracking. So, these are the techniques which are used to measure flow velocity and which are non-invasive in nature. Now, question is why you are going to discuss about laser Doppler anemometry. Laser Doppler anemometry relies on the measurement of velocity on the that are image based, in which we need to have a source of light. Now, the word itself is the word itself is sufficient to know that in a laser Doppler anemometry the light source is laser. Now, as I said that laser Doppler anemometry is a non-invasive technique, there are a few advantageous features. So, when we talk about LDA, this instrument, this measurement techniques, so this measurement technique which is having a few advantageous features. So, which is having a few advantageous features. Number 1, do not disturb the flow field. We have discussed that we can have measurement of flow parameters using probe, we can have measurement of volumetric flow rate using flow obstruction flow meter. In fact, we have seen in the last class that we can measure velocity using hot wire or hot film. In all these cases, we need to insert the instrument, we need to insert the object in the flow field. Now, when we insert the object in the flow field, definitely that placing or imposition of that particular instrument in the flow field will try to disturb, and as a result we may not get the accurate actual velocity which you are going to measure from using that instrument. So, from that perspective, this technique, that is laser Doppler anemometry, is having advantage. So, that is because this technique do not disturb the flow field, and that is why the word non-invasive is came. Another important is that this technique can be used to measure flow velocity in situations. So, it can be measured, this technique can be used to measure the flow velocity. So, when we talk about flow velocity, as I said, this is used to have point flow measurement. So, this is used to measure flow velocity at a point. Now, measure the flow velocity in situation where fluid is acidic, if the fluid is corrosive, and flow is contaminated with different foreign particles. So, again if you would like to compare this technique with the other available techniques that we have discussed, that hot film, hot air, mechanical probe, in all these cases we cannot, even if we use I mean it will, the corrosive nature of the fluid, acidic nature of the fluid will try to, rather it will try to damage the measurement points. If it is mechanical probe, that will try to clog the point, clog the hole. If it is hot air, it will try to tear the wire. So, the presence of foreign particle and the different fluid properties like acidic, corrosive, these are not, I mean these properties are not important, rather we do not consider whether the fluid is acidic or corrosive or fluid is contaminated while you are using LDA to measure the flow velocity. So, these are the a few advantageous features which are associated with the LDA technique. Now, as I said that LDA, that is laser Doppler anemometry, and light source is the laser. Now, why we are using laser light? There are many other sources of light, instead we can use any radioactive wave, but we are using laser because laser light is also having a few important points, rather important favorable points that we should discuss now, that laser light is monochromatic, penetration depth is higher. Number 3, signal to noise ratio is also higher. So, accounting all these 3, rather all these important points, we are using laser as a light source. Now, we need to know what is the basic principle of measuring flow velocity using the LDA technique or laser Doppler anemometry. So, the basic principle that we need to know of LDA. So, now we will discuss the basic principle. So, up to this time we have understood laser Doppler anemometer is used to measure point velocity. This measurement is non-invasive, this measurement is not rather do not disturb the flow field, and using this technique we can have flow measurement, rather measurement of flow velocity when fluid is toxic, fluid is acidic, fluid is corrosive, and if the flow is contaminated. So, we need not to consider at all. If we try to measure flow velocity using other instrument like mechanical probe or hot film, then this kind of contaminated flow, corrosive nature of the fluid will try to destroy the lifetime of those instruments. But this is not an important point that we should consider when we are measuring flow velocity using laser Doppler anemometry. Now, As I said that this technique uses laser as a light source, and then light is incidented on a object, and from there we receive one frequency. So, when a light is incidented on an object, so we have a frequency, and when the light is incidented of the object, that light will be scattered. Now, and from that object we also try to capture, receive the frequency. Now, the basic principle is LDA is that I am writing now that this LDA, that is laser Doppler anemometer. The word Doppler is there, so we will be using Doppler effects. We have studied Doppler effects in our class 2 level 10 plus 2 level physics. So, we have seen what is Doppler effect, and again today we will discuss why this Doppler effect is coming into picture when we talk about flow velocity measurement using LDA. So, LDA technique is that Doppler effect, this techniques invokes the Doppler effect two times, right. First when the light, rather incident laser light, which is characterized by frequency Fi and wavelength lambda I, when the incident laser light impinges on a moving particle or object. So, the laser Doppler anemometer technique I can say this technique, it is technique, laser Doppler anemometer technique invokes the Doppler effect two times. First, when the laser light, incident laser light, which is characterized by the frequency Fi and wavelength lambda I, impinges on a moving particle, and second is when the light with frequency other than Fi is scattered from the moving particle and received by a receiver or detector. So, this is the basic principle. We incident laser light on a moving particle, then and we know the frequency and wavelength of the moving particle, and then second is when the light is being scattered by the particle, by the moving particle, the scattered light and that frequency is different than the Fi, and that frequency is received by a receiver or detector. So, now this is the basic principle. So, now we will taking an example, we will see how we can really measure, rather we can use this technique to measure the flow velocity, and till now we have discussed about the laser light frequency, and we will see that we can correlate the measured frequency with the fluid velocity. So, I can show you that say we have a laser source. So, this is a laser source, and the laser light is taken into a splitter, say this is beam splitter, and the light is divided into two parts and taken into a lens, and then from lens we can focus the light in a zone of our interest. Say if it is if it is the zone of our interest and we are focusing the laser light, and the light which is scattered is again taken into a lens, and that is collected by a receiver. So, this is receiver. So, this is lens 2, this is lens 1 and this is receiver. So, say we would like to measure the flow velocity, and this is the confinement. So, this is fluidic confinement, and we would like to measure the velocity of the fluid that is flowing through this confinement using this laser Doppler anemometer technique. So, what is done? There is a laser source, light is coming, light is taken to a beam splitter essentially to split the light, incoming light into two parts. The splitted now lights are taken into a lens essentially to focus that light on a zone which is the zone of our interest, and then from there we again the scattered light is taken by into a lens, and finally the frequency or length or light or wave that is received by the receiver. Now see, I can tell you now when there is no any particle, then the light is coming, say I can tell that there is no any particle. So, light is coming and the light will be received by the receiver. So, there we will get one kind of frequency at the receiver, frequency of the receiving end. Now, say another condition where I am giving a few tracer particle here, these tracer particles, and these tracer particles are seeded in the fluid and particles are neutrally buoyant. So, the tracer particle, so case 1 I can write now, case 1 when there is no particles in the fluid, and case 2 when tracer particles, sometimes they are known as marker, are seeded in the fluid. So, marker means they are used to mark the phases. So, phase marker, velocity of the phase we want to measure. So, basically the tracer particle also known as phase marker, that is velocity of the phase we want to measure. Fine. So, now tracer particles when the tracer particles are seeded in the fluid, now the important characteristics of the tracer particle will be the density of the particle. So, the tracer particle I am writing the tracer particle density is rho s, and this is equal to the fluid density rho f, and tracer particles are very small. So, tracer particles which are seeded, they are very small and density of the particle is equal to the density of the fluid, so that they can follow the flow. Now, that is they are neutrally buoyant. So, the particles which are seeded, they will largely follow the flow direction and density is equal. So, these two are the important, I can say points we need to consider when we are seeding a tracer particle to essentially to measure the flow velocity. Okay. Now, if I go back to my previous slide, I can tell when there is no particle, of course, the receiver will receive signal, the light which is falling on the object from the laser source, and receiver will definitely receive a signal. In that case, if the signal frequency is f, and the second case when we seeded a few particles, and the particles when they are seeded, now when the light is incidenting on the particle, they will try to transmit in different direction. Now, there will be transmission directions which are in the direction of the receiver. So, when the particles are seeded in the fluid and particles are neutrally buoyant, they will follow the fluid motion. When the light is now falling on the particles, there will be a scattering of the light by the particle in different direction. There will be direction of the scattered light which is in the direction of the receiver. Say in that case, the signal received by the, this is for the case 1, and in that case f plus fs, and say this is for the case of 2, that is when a fluid is having a few seeded particle. Now, obviously this f plus fs, so f plus fs, so this is the frequency received by the receiver when tracer particles are seeded, while f is the frequency of the signal or light received by the receiver when no particle is there in the fluid. That means, therefore, this f will not be equal to f plus fs, and this fs is a shift in frequency. This f plus fs may higher than f, may lesser than f, that will depend upon so many things that we will discuss now, but what we can say that the frequency received by the receiver in absence of tracer particle will not be equal to the frequency received by the receiver in presence of the tracer particle, and this fs is nothing but the phase shift, and this fs is known as frequency shift or additional shift. Or shift in frequency Now, this shift in frequency can be directly correlated, this Fs shift, frequency shift of course, this shift can be directly correlated to the fluid velocity, and that is what we will now discuss. So, that means what we are using, we are using scattering of light by particle for which we have a shift in frequency. So, that is the Doppler effect, and that is how Doppler effect is coming into picture when we talk about laser Doppler anemometry. So, that means scattering of light by the particles, scattering of light by the particles, and as a result of which phase shift or shift in the frequency, I can say shift in frequency, and this is the Doppler effect. So, that is how Doppler effect is coming into picture, because what we are doing, we are using the scattering of light by the particle which are seated in the fluid, and from there we are trying to measure the shift in frequency, and from that shift in frequency can be directly correlated with the fluid velocity. Mind it, the particles which are seated in the fluid are neutrally buoyant, the density of the particle is the density of the fluid. So, the particles are expected that the particle will largely follow the flow direction, and from there we can correlate the fluid velocity. So, next we will see how we can now calculate the that shift, and that shift can be correlated with the fluid velocity. So, if we consider there is a object and a light or wave is incidented on that object. So, this is the object, and that object say is moving in this direction with a velocity v. So, the object is moving. So, this is the object which is moving, and light is incidented on that object. So, say the light is falling on the object is moving v. So, the object will try to scatter the light, and the light scattered lights, that is say received by the receiver. So, this is the receiver. So, this is scattered light. And this is the moving object, and this is light or wave incidented on the object, right. And if we considered the wavelength is lambda I and frequency is Fi of the incidented light, right. So, object is moving in the with a velocity v, and light is falling on it having frequency Fi and lambda I, and there will be scattering, and the scattered light is received by a receiver. Now, we know that F into lambda is nothing but c, that is the speed of the light. Therefore, Fi will be equal to c by lambda I for this particular case. For the incidented light, that we can write. So, Fi is equal to c by lambda I. So, this is what the frequency of the incidented light. Now, particle is moving with a velocity v. So, the frequency of the light which is falling on the particle, that we need to calculate. So, if we try to calculate, I can write over here. Now, say frequency of the light falling on the object is Fp, say this is Fp on the object or particle, say on the particle. Or particle Fp, then this Fp will be, it should not be C by lambda I, it should be C dash by lambda I, because particle is now moving, it is not stationary. So, the light which is falling on the particle, the light has frequency Fi, that is C by lambda I, that is what we know. We have assumed the frequency of the light is Fi. Now, the frequency of the light, the frequency received by the receiver in presence of particle. So, the receiver will now receive a frequency, and that is Fp, and that is C dash by lambda I. So, if the particle is not there, then the receiver will receive the frequency that is equal to the Fi. But now, because of the presence of the particle which is moving in the with a velocity v, the receiver will now receive a signal that is Fe, that is C by lambda I. Now, that is nothing but I can write C minus V by lambda I, and I would like to put an unit vector I over here, because the particle movement, if it is in the direction of the light, incoming light and particle, both the direction of both the light and incoming light and particles are in the same, then the unit vector will be -1, but unit vector will be 1, but if they are in the opposite direction, so if the particle moves in the direction from where the light is coming, then the unit vector will be -1, and that will be C plus Vi. So, we can assume as if someone is creating a sound, say someone is creating a sound from this source. So, this is source, he is creating a sound, and sound wave is coming in this direction, and someone is also moving from away from the source, and with time what he or she will face, that with time the sound waves will be reduced. So, that means the source and the object, both of them are moving in the same direction. So, that source is not moving, but the light which is coming from the source, the direction of the light and the movement of the object in the same direction. So, with time the strength of the frequency will reduce, and that is the C minus Vi. Now, if they are in the opposite direction, that means if the light is coming from a source and object is also moving towards the source, then that will be C plus Vi. So, that means the strength or the frequency will keep on increasing. So, now this is C minus Vi by lambda I, so that we can write. So, when we know the frequency Fp, then we like to calculate lambda p. So, this lambda p is essentially the phase shift, this is the shift. So, lambda p is the frequency, wavelength lambda p is the wavelength. We need to know lambda p. Lambda p, and that is wavelength of the light fall on the particle. Right, the frequency of the light. So, lambda p will be equal to C by Fp using that relationship. Now, if I plug in the value of C by Fp, that is C into lambda I divided by C minus V into unit vector. So, this V is a vector. So, this is V, and so this will be unit vector. So, this is lambda p. Now, So, that means now object light is falling on the object will try to scatter, object is moving in the direction v, in the direction with a velocity v. So, we will get a frequency, and that is what we have calculated, and we have calculated the wavelength. Now, if the frequency of the incident light, rather if the source is moving, so now we need to receive a signal by the receiver when as if the object is moving. So, now the light that will be transmitted by the kind of, I can say, so this is lambda p, right. Now, the particle is moving with the fluid. So, the particle velocity is equal to the fluid velocity, light is falling on it, it will scatter light, and we have calculated wavelength of the light fall on the particle lambda p. Now, the light is now moving, the object is now moving, so that as if now we will receive the signal from the light from the object by the receiver. So, now object is moving, that is as if the source is moving. In that case, what will happen? So, if we the wavelength of the signal when source is moving. So, now question is, as if the light is incidented on the particle will scattered, and we have calculated the frequency, the wavelength of the light fall on the particle lambda p, that is c by f p. If there is no particle, the receiver will receive f I, that is lambda. Now, the wavelength which is falling on the particle is lambda p, but wavelength that will be received by the receiver when particle is present, that is lambda s, and that is again c double prime, say c double prime by f p. This c double prime again it is c minus v j. I again do not know where, because again I am using the unit vector j, and again we can apply the same argument. If the direction are in the same direction, if they are in the same direction, j will be plus 1. If they are approaching towards them, then it will be minus 1. So, c minus v j by f p, and if I put the value of f p from the previous equation, then lambda s will be equal to, rather I can write c minus v j lambda I by c minus v I. So, this is the expression of the lambda s when source is moving. Again I am telling, when there is no particle, receiver will receive a signal that frequency is f I. When the particle is there, because of the movement of the particle, the wavelength which is falling on the light on the particle, that will be lambda p, that you have calculated. Now again wavelength with the particle will scatter a light, the frequency of the light that is being frequency rather of the signal or light that is being received by the receiver will be lambda s, and that is c double prime by f p, and that is nothing but c minus v j by f p, and we have calculated this. So, I can say what will be now f s. So, what is f s? So, frequency when source is moving. So, that will be equal to c by lambda s, and that is nothing but c into c minus v I divided by lambda I into c minus v j. So, what is the shift in frequency? That is very important. Now, f d, that is the Doppler effect. So, f d, that is the Doppler effect equal to f s minus f I. So, the amount of light, how much incidented on the object, how much being scattered by the object. So, this is the incidented, and this is how much light scattered. And this FD, if we do algebraic manipulation, we can write this is nothing but C into C minus Vi divided by lambda I into C minus Vj minus Fi is equal to C by lambda I. So, if I take now C by lambda I out, then we can write C minus Vi minus C plus Vj. These are the unit vectors by C minus Vj. So, this is C by lambda I into Vj minus Vi by C minus Vj. So, ultimately we can write Fd, that is Doppler shift, is Vj minus Vi C by lambda I by C minus Vj. So, you can see the Doppler, that is we have written over here the Doppler effect. Now, the change in frequency can be directly correlated, that is Fs, that is what we have discussed at the beginning of this class, that Doppler effect, the shift in frequency, that can be correlated with the fluid velocity. Now, in most of the applications, most of the application I can say almost for all the applications, if I write that light intensity of the laser is, V, the velocity of the fluid is much less than C. That is true for almost all the applications, for all the applications. If that is the case, then Fd is equal to, I can write C by lambda I Vj minus Vi divided by C. So, this is equal to V into J minus V into I divided by lambda I. So, we can see that the Doppler shift, that is what we told at the rather in the beginning of this course, this Doppler shift, Doppler effect, shift in frequency is directly related to the fluid velocity, right. So, that means Fd is proportional to the function velocity. So, what we can say, that means we have discussed light is incidented on object. If there is no particle, the signal received by the receiver will be Fi. In presence of an particle which are tracer particle, which are neutrally buoyant, density is equal to the fluid density. That means the particles are following the bulk flow. Now, in that case, if the light is incidented on the particle, the light will be scattered by the particle. In that case, we have calculated the frequency of the light which is falling on the particle, and now source is moving. In that case, the signal received by the receiver, again we have calculated by Fs. So, now Fs minus Fi, that is nothing but the Doppler effect that we have calculated, and we have seen that the Doppler effect, that is shift in frequency, that can be captured by the receiver. Receiver is nothing but photomultiplier tube. So, this receiver we have shown in the schematic. This receiver is essentially photomultiplier tube. So, when light is received by this photomultiplier tube, the photon, it absorbs photon energy, and that energy is getting converted to the current, and from there we can calculate the frequency. So, this photomultiplier tube, so this is the receiver. So, it receives photon, that energy is converted to the current, and from there we calculate frequency. So, now by calculating the frequency from the receiver, we can directly correlate what will be the velocity of the fluid. So, this is what is the basic principle of the LDA technique. The mathematical analysis that we have done, that is not particular, this is a generic analysis, this is valid for almost for all the light image based technique. Now, to summarize what we have discussed today, that is very important, that I can write for the sake of completeness that principle. So, LDA, the principle that is tracer particles are used or seeded Doppler effect is used to measure flow velocity measurement, that is point velocity measurement. Laser source is used for incidenting light on the object. Scattered light is detected by the PMT or receiver photomultiplier tube, and we calculate shift in frequency, and this shift in frequency is which is directly related to the fluid velocity. So, this is the basic principle of using laser Doppler anemometer to measure the flow velocity, that is the point velocity. We have discussed that flow measurement is the volumetric flow measurement, point velocity measurement, and the determination of the flow streamlines. We have discussed about the techniques which are used to measure volumetric flow rate. We have discussed about the techniques which is used to measure point velocity, that is hot wire and hot film, and today we have discussed about LDA. And today we have discussed about the basic principle by which we can measure flow velocity, and we have seen this is completely a non-invasive technique and which is used in situation where fluid is corrosive, acidic, and fluid is highly contaminated. And since this is not immersed or this is not placed in the flow field, they do not disturb the flow field, and as a result the measurement which you are obtaining using this technique is almost accurate one. So, today we have discussed about another important technique which is used to measure the velocity at a point, and we have discussed about the basic principles with small mathematical analysis, that how we can calculate the flow velocity, rather how we can calculate velocity in with the frequency of the light which is falling on the object. So, with this I stop my discussion today and will continue my discussion in the next class. Thank you.